In 1964, a series of crisp, theory-forging papers, one by Peter Higgs, another by Francois Englert and Robert Brout, and complementary work from Gerald Guralnick, C.R. Hagen, and Tom Kibble, proposed a mechanism explaining how gauge bosons acquire mass while preserving the symmetries of quantum field theory. Their idea implied a new quantum of excitation, a scalar boson, later called the Higgs boson, which became the missing linchpin of the Standard Model and the key to why the W and Z bosons are massive while the photon stays massless. For decades, it remained a theoretical jewel without experimental proof, sparking a globe-spanning hunt. Experiments at SLAC, CERN's Super Proton Synchrotron, Fermilab's Tevatron, and many collider and fixed target studies pushed the limits but never produced conclusive evidence for a Standard Model Higgs. The stakes were enormous. Confirming the Higgs would validate the electroweak theory and the mechanism proposed in 1964. Failure would have forced a radical rewrite of particle physics. To settle the question, CERN built the Large Hadron Collider, a 27-kilometer ring straddling the Franco-Swiss border near Geneva, designed to collide protons at unprecedented energies. The LHC first circulated beams in September 2008, and by 2010 was delivering high-energy collisions to its experiments. Two massive general-purpose detectors, ATLAS, a toroidal LHC apparatus, and CMS, compact muon solenoid, sit in caverns about 100 meters underground to capture collision debris with exquisite precision. By the late 2000s, the LHC and these detectors embodied a high-stakes gamble, either affirmation of a golden theory or a doorway to new physics. Building the LHC was a decade-long brass and steel feat. It culminated on September 10, 2008, when the first beams circulated the 27-kilometer tunnel under the Franco-Swiss border near Geneva. But on September 19, 2008, a catastrophic electrical fault and magnet quench tore open cryostats and forced a year of repairs and a rigorous safety redesign under CERN Director General Rolf Hoyer. Recovery was methodical. The machine was recommissioned, cryogenics and interconnects were reinforced, and by March 30, 2010, the accelerator achieved stable proton collisions at a center of mass energy of 7 TeV, launching a 2010 run that expanded into a high statistics campaign through 2011. ATLAS, led at the time by spokesperson Fabiola Giannotti, and CMS, led by Guido Tonelli in 2011, collected data with two very different detectors that nonetheless sought the same quarry, the Standard Model Higgs. By the end of 2011, each experiment had amassed roughly 5 inverse femtobarns of integrated luminosity. The 2010 to 2011 runs produced the first tantalizing localized excesses clustering near 125 GeV, most visible in the diphoton and 4-lepton channels. Those excesses were statistically fragile and demanded exhaustive internal scrutiny. Teams used blinding procedures, predefined analysis strategies, sideband background estimates, control regions, and Monte Carlo cross-checks. Analysis review committees and internal referees tore apart selection cuts, energy calibrations, photon and lepton identification, and pile-up corrections to hunt down any artifact. Independent detector designs and independent analysis pipelines in ATLAS and CMS provided a crucial cross-check against shared systematic errors, while statisticians insisted on explicit treatment of the look elsewhere effect and on combining channels only after accounting for hidden trials. Subscribe. Maybe it would have nudged those stubborn excesses into a discovery. The result was a tense, disciplined build of momentum, tantalizing hints that could not yet be called a discovery, a mountain of cross-checks that survived scrutiny, and a clear path into a decisive 2012 run that would either confirm the 125 GeV whispers or see them fade. The 2012 run raised the stakes. After a technical stop, the LHC returned at a center of mass energy of 8 tera-electron volts and delivered a far larger trove of collisions to the caverns beneath Geneva, and both ATLAS and CMS dug in. Signals that had been mere whispers in 2010 to 2011 sharpened into persistent, repeatable structures in the diphoton, gamma-gamma channel, and in the ZZ to 4L channel, with narrow invariant mass peaks clustering near 125 giga-electron volts. Every candidate event was chased down. Photon energy scales in the electromagnetic calorimeters were recalibrated with Z to EE and pi zero samples, Muon momenta were cross-checked against J psi and Z resonances, and tracker alignment and vertexing were stress-tested to exclude hidden biases. Analysis teams kept strict blinding where possible and extended blind cross-checks to control regions, while independent analysis pipelines, different reconstruction algorithms, alternative background models, and orthogonal selection cuts converged on the same excess. Statisticians ran profile likelihood fits, computed p-values, and used the CLS method to set limits. They painstakingly quantified systematic uncertainties from theory cross-sections, detector response, and pile-up, and they evaluated the look-elsewhere effect to separate local blips from a true discovery. As datasets accumulated, local significances in the high-resolution 4-lepton channel and the high-rate diphoton channel crept upward, and combined channel fits began to approach the coveted 5 sigma threshold. Internal review committees demanded reproduction of results with blinded recomputations and toy Monte Carlo ensembles, and external seminars and preprints were prepared with unusually exacting conservatism. The mood at CERN turned from cautious curiosity to taut expectancy. Independent collaborations, independent detectors, independent analyses, and a steadily intensifying statistical chorus all pointed to the same unmistakable anomaly near 125 giga-electron volts, setting the scene for a decisive public reckoning that neither team took lightly. In late June and in the first days of July 2012, the work became surgical. Teams completed profile likelihood fits, froze selection criteria, and ran final ensembles of toy Monte Carlo to quantify rare fluctuations. Systematic reviews consumed long days. Calorimeter energy scales, muon momentum calibrations, tracking alignment, pile-up corrections, and luminosity determinations were re-examined. Theory uncertainties on production, cross-sections, and branching ratios were revisited, and correlation matrices between channels were constructed and stress-tested. Analysis review. Committees in ATLAS and CMS demanded independent reproductions, blind replays, and exhaustive closure tests. Any residual discrepancy was traced to instrumentation, simulation tuning, or statistical oversight, then corrected or constrained. Parallel to the technical closure, collaboration leadership coordinated messaging. Internal notes were finalized, plots for public seminars were vetted for clarity and consistency, and legal and press offices synchronized timing. The final masses and significances came from combined channel fits. Narrow invariant mass peaks in the high-resolution ZZ Arrow 4L channel and the high-rate gamma-gamma channel clustered near 125 GE5 in both detectors, and combined local significances reached the threshold particle physicists require to claim discovery. On July 4, 2012, in the CERN auditorium in Geneva, the scene was precise and rehearsed. Director General Rolf Heuer opened. ATLAS spokesperson Fabiola Gianotti presented a pronounced excess near 125 GE5 across independent channels, and CMS spokesperson Joe Incandela followed with an independent analysis that echoed the same signal. Each talk showed independent detector evidence, consistent mass estimates, and compatible signal strengths within quoted uncertainties, and both teams reported local significances at the discovery scale. Those twin, concordant presentations, born of weeks of grueling cross-checks and coordinated preparation, converted a persistent anomaly into a claimable discovery and set the stage for a public declaration that reverberated through laboratories and headlines worldwide. On July 4, 2012, in CERN's cavernous auditorium in Geneva, a long, meticulous buildup ended in an electric instant. Director General Rolf Heuer opened the seminar. ATLAS spokesperson Fabiola Gianotti presented a clear excess near 125 giga-electron volts and announced the observation of a new boson, and CMS spokesperson Joe Incandela followed with independent evidence that echoed the same signal. The room exploded from taut silence into roaring applause and stunned embraces as plots of diphoton peaks and 4-lepton events flashed on the screens. Television crews, laptop feeds, and phone cameras turned the seminar into a live spectacle seen by millions. Newsrooms in London, New York, and Tokyo cut to the feed, social media and front pages erupted, and CERN's webcast recorded unprecedented traffic. Scientists on stage and in the audience balanced exhilaration with discipline, repeatedly calling the particle Higgs-like and stressing the urgent need for measurements of spin, parity, coupling strengths, and decay modes to confirm whether it matched the standard model scalar predicted in 1964. The announcement crystallized decades of theory, brass and steel engineering, and international collaboration into a single public moment. It ignited a global media frenzy and immediately refocused the community on the next essential task: precise characterization. That urgent program would set the field's agenda for years to come. Within months of the July 4, 2012 announcement, ATLAS and CMS launched rapid follow-up measurements to probe the new particles' spin, parity, and coupling strengths. By 2013 through 2015, the results strongly favored a spin-zero, even parity boson with couplings broadly consistent with the standard model, although searches for deviations intensified. On October 8, 2013, the Nobel Prize in Physics was awarded to Peter Higgs and Francois Englert for their 1964 theoretical prediction, a high-profile recognition that echoed across laboratories worldwide. The Large Hadron Collider then sustained an ambitious program of higher energy runs, precision measurements, and targeted searches for additional scalars or unexpected phenomena, turning one discovery into a long-term experimental campaign. Technological spin-offs from superconducting magnets and detector instrumentation to the worldwide LHC computing grid have rippled into medicine and industry. The discovery became a powerful model for large-scale international science, rekindling public fascination and drawing new talent. Yet central mysteries remain: naturalness, dark matter, and vacuum stability, keeping the quest urgent and ongoing.